Let's talk about the preparation of alcohols via Grignard reagents. This is a Frenchman's last name. The reagent has been named after him because he invented it. So let's look at how we prepare a Grignard reagent. What we need is some alkyl halide. Typically, we might say ethyl chloride or ethyl bromide would work. And we're going to add to that magnesium metal. So this is literally magnesium that's been crushed up into small pieces. And the metal is added to the reaction flask. Typically there is some ether solvent present. And what happens is that the magnesium inserts itself into the carbon to halide bond. This would be a bromide or a chloride. Most of the time it works best with bromine. So we end up with RMgX, or we end up with ethyl magnesium bromide. And in this case, we know that the magnesium adopts a 2+ oxidation state because of its location on the periodic table. We know that the bromide has a -1 oxidation state because that's what halides normally have. So in this case, we then get a minus oxidation state for our R group, and this gives us essentially the equivalent of ethyl anion or whatever other R group you have. So you can do this with any alkyl halide, primary, tertiary, or secondary. So it doesn't matter the shape of it as long as it has a bromide or sometimes a chloride. So now I essentially have an ethyl anion that I can use in a reaction. So this is a good nucleophile, and as you might guess, it's also a great base. So we need to be careful when we're running Grignard reactions to exclude water or any other source of reasonably acidic protons. So let's look at a mechanism that this could undergo. Let's look at acetone to start with. And we know that the oxidation state of acetone is 2+. I'm going to react that with ethyl Grignard. So this is how we would draw that. Excuse me. And in the second step, I will add some water. It's very important that you identify two different steps here, and I'll show you why in a second. So what we can do is we'll draw a line from the magnesium-carbon bond, which is our nucleophilic portion, towards the acetone carbonyl carbon, and that gets us to this species, which is an alkoxide. It now has 3 bonds to that central carbon. And in the second step, addition of water, let's draw it like this, we can draw a proton transfer step. So this is nucleophilic attack right here, and now we're going to do a proton transfer, just like we learned way early in first semester organic chemistry. We've turned a ketone into a tertiary alcohol. So here's a way to synthesize tertiary alcohols. And if I calculate the oxidation state here, I would have a carbon with a single electron from each of the carbon-carbon bonds, 0 electrons from the oxygen bond. So this is 1 fewer electron than normal. This would have a +1 oxidation state. And so you can see that we went from +2 to +1, so we've reduced it by 1 oxidation value. And as I said before, H2O needs to be added in the second step. And why is that? Let's look at that. Equilibrium. Remember, whenever we have a question about, why can't we mix these two acids and bases together, or what's the issue here, it's very helpful to draw an equilibrium. So here's my ethyl Grignard. Here's my water molecule. Here's an equilibrium where we would essentially end up with an H on that carbon. So this is also the same as CH3. Make sure that you can understand how these are the same molecule. I'm just drawing this H because I need to show that it came from the water molecule. And we'd have MgBr, which is a cation. So my charges are balanced and my equation is balanced. And so now if I look at the pKa's of the acids, I have a pKa around 16. The pKa of ethanol, or I'm sorry, ethane, is 50. So there's a massive difference in pKa, which means it's not going backwards. This reaction is irreversible, and it's extremely irreversible. So I can make this arrow a little bigger to emphasize the fact that it ain't going to the left. We're going to make ethane here like there's no tomorrow. And in fact, if I did mix these two together, there's enough energy given off to ignite the ethane. So I would get a fireball here, not just a synthesis of ethane, but I would get a fireball. And so this takes an expensive Grignard reagent. Remember, it takes a lot of effort to make a Grignard because I have to get the magnesium. I have to make sure that I have a water-free environment or an acid-free environment. So I need clean glassware, I need dry conditions, anhydrous conditions. And if I simply protonate ethyl Grignard to make ethane, I have a very expensive synthesis of ethane. Okay, so if you do not show the 1 and the 2 steps here, I'm going to assume you mixed everything together. You achieved a nice fireball for a few seconds. It was fun, it was exciting. Hopefully you didn't get burned. But you didn't achieve your goal because you produced ethane, which is not going to react with the ketone. So you must have a 2-step process here. Otherwise all you've done is protonate your expensive Grignard reagent. Alright, so Grignards can react with a number of carbonyl compounds. We showed you a reaction with a ketone, so how about with aldehydes? Here's an aldehyde. I'm going to use methyl Grignard in this case. Remember, essentially any compound you can make that is an alkyl bromide or an alkyl chloride, you can turn into a Grignard. All you have to do is add magnesium to it. And I'm going to have my 2 steps here. I'm going to look at the oxidation state. You can calculate that, but it is +1. So remember that our Grignard will add to the carbonyl carbon and end up with an alcohol in that location. And I didn't need to draw this hydrogen here. I'm just keeping it around so that we see where it went. It was unaffected by the reaction. This oxidation state is 0, so you can calculate that and see that we have indeed reduced our compound. This is a secondary alcohol, so we know that aldehydes produce secondary alcohols when reacted with Grignard reagents. There's another way I could make this aldehyde through a different Grignard reagent, and another way I could make this secondary alcohol through a different Grignard reagent and a different aldehyde starting material. See if you can figure that out, and then I will show you in a minute. So you may have noticed that the first Grignard reaction resulted in the formation of that carbon-carbon bond. So here on our secondary alcohol, there is another carbon-carbon bond that we could produce via a Grignard reaction if we so desired. So let's produce that one. We'd have to observe that the aldehyde that we'd start in this case would essentially have a methyl group and a hydrogen on it. So let's draw that. So there's the new aldehyde starting material. And I'd want to react it with a certain Grignard that would make the second of my green arrowed indicated carbon-carbon bonds. So that would be a 3-carbon Grignard. I need propyl Grignard in this case. 1, 2, 3, Mg, Br. So if I mix those two together, followed by addition of water, so let's just indicate that the second step here would be water, I should be able to produce the same secondary alcohol. So here we see that there are different ways to produce the same desired product, and none of them are better or worse than the other unless I direct you to, say, use aldehyde like this instead of the 2-carbon aldehyde, and then you'd have to choose the proper way. But if the goal was just to make this secondary alcohol that's in the middle here, you can do that 2 different ways. In fact, you could do that via a reduction of the appropriately shaped ketone by adding just that H as well. So there are 3 ways to make this secondary alcohol via the reduction of a carbonyl compound. So let's look at reaction with esters. So here is a simple ester, and we're going to react methyl Grignard with this ester. If you remember reduction of esters using hydride reagents, we had the opportunity to add 2 H minuses, and in this case it's no different. We have the opportunity to add multiple Grignard reagents. So let's explore why that might be. So the first thing I'm going to do is put this bond in here so that I can draw the mechanistic arrows. So this would be nucleophilic attack. That's always going to be the first thing that we get when we react a Grignard reagent. And of course that produces our alkoxide intermediate, and we've added the Grignard as the new methyl group right here. As we saw with hydride reduction, we could lose the OCH3-, the OR group portion of the ester can be lost now because we are in quite basic conditions. Remember that Grignards are extremely good bases, so producing this relatively strong base is not really a problem. Okay, so this strong base here is produced as the leaving group. Normally that would be frowned upon, but because we're already in such good, strong basic conditions in our flask, producing this base is not a problem. Now you see how we have the opportunity to add another Grignard reagent to our newly formed ketone. This is actually more reactive than the ester. And so we can take another equivalent of the Grignard and produce a alkoxide product. So there's my first methyl, here's the second methyl. Now you see I have an alkoxide product here. I can't add any more Grignards to this. Really the only thing I can do is protonate it to produce the product. So the product in this case is a tertiary alcohol. And this is a proton transfer step, and let me use water here to draw my arrows properly. And so I need to specify excess, and we'll literally use the two letters X and S to just quickly show excess methyl magnesium bromide. So in this case I use more than one equivalent. I could write 2 equivalents if I want to, but typically we just write excess. You can use the word excess, you can write X and S, the 2 letters. We need to indicate that we have 2 equivalents or more of this Grignard reagent so that we can add to this ketone. If we don't have 2 equivalents of the Grignard reagent, we'll get a whole mix of products, some of which would have 2 additions of the Grignard, and some would be starting material that didn't get to react because we ran out of Grignard reagent. So that is the 3-step process of, actually I'm sorry, it's a 4-step process of Grignard addition to an ester.